All right, welcome everyone. Today we are about to go on a journey, a 5-lesson journey really, into the hidden geometry of, well, pretty much everything. We're going to build a totally new kind of intuition, one that helps us see the strange, beautiful mathematical shapes that power everything from your phone's facial recognition to the quantum computers of tomorrow.
So let's kick things off with a question that sounds kind of simple, right? Can a sphere leak out of a box without breaking it? I mean, in our everyday 3D world, you'd say, no way, it's impossible. But what you're about to see is that in higher dimensions, our intuition doesn't just bend, it completely shatters.
And this is where it gets super weird. Imagine you've got a sphere in the middle of a box, held perfectly in place by other spheres packed into every corner. Now, watch what happens as we crank up the dimensions. In 9 dimensions, that middle sphere gets just big enough to kiss the sides of the box. But in dimension 10, it literally pokes out of the box. And by dimension 100, it's enormous, sticking way out even though it's still trapped by those corner spheres. This is our first big clue that high-dimensional space just doesn't play by the rules we're used to.
And that right there, that's the heart of the problem we're tackling. You see, the intuition we've built our entire lives to navigate the physical world, it just breaks when we face the challenges of big data, of AI, of quantum mechanics. To understand these fields, we need a whole new mindset.
So here's the game plan. This is our roadmap for building that new way of thinking. First up, we'll explore the shocking emptiness of space in the vanishing sphere. Then we'll learn to find the shape of data that's hiding in all that emptiness. After that, we'll dive into the butterfly effect to see how geometry models chaos, before we enter the quantum arena, where computing itself is a geometric puzzle. All right, lesson 1, the vanishing sphere. Here, we're going to come face to face with the most fundamental, most mind-bending property of high-dimensional space. It is almost completely empty.
This whole idea has a name, and it's a pretty dramatic one: the curse of dimensionality. See, as you add dimensions, the volume of a space just explodes exponentially. A sphere that seems to fill up a box in our 3D world becomes just a tiny speck of dust in a 100-dimensional box. Its volume, compared to the box, basically shrinks to 0. So where did all that space go? It's all hiding out in the corners.
To really put this into perspective, just imagine trying to map out a 100-dimensional space. If you just divided each dimension into 10 little segments, you'd need 10 to the power of 100 grid cells to cover it. That's more cells than there are atoms in the entire known universe. Just let that sink in. Our old ways of searching for things just completely fall apart.
And you're not just going to take my word for it. In the first Python exercise for this lesson, you'll actually prove this to yourself. You'll run what's called a Monte Carlo simulation, just throwing random points into a high-dimensional box, and you'll watch with your own eyes as the number of points that actually land inside that central sphere drops to pretty much 0.
So, that brings us right into lesson 2, the shape of data. Okay, so if these spaces are so ridiculously huge and empty, how do we find anything useful in them at all? Well, the trick is realizing that real-world data isn't just splattered around randomly. It has a secret shape.
I mean, think about your phone for a second. A simple, tiny 64 by 64 pixel image of your face is actually a single point in a 4,096-dimensional space. How on earth does your phone sort through that absolutely astronomical space to find you in a split second?
The secret is something called the manifold hypothesis. It's the idea that real data, like all the possible pictures of your face, doesn't fill that entire 4,096-dimensional space. No, instead, it all lies on a much simpler, lower-dimensional surface, a manifold that's embedded inside it. The best way to think about it is like this. Imagine a giant flat map. The data isn't scattered all over the map. It's just following a single winding road. That road is the manifold.
And this is so cool. In the second Python exercise, you'll actually see this happen. You're going to use an algorithm called UMAP to take a whole data set of faces, all in 4,096 dimensions, and squash it down to just 2. And you'll literally watch as these distinct clusters, these identity manifolds, just pop right out of the chaos. Each one is the unique geometric signature of one person's face.
And this idea is so powerful. It's not just for faces. It's the exact same principle that let us talk to the Voyager spacecrafts. To make sure the messages didn't get corrupted by cosmic rays, engineers basically mapped each message to a specific point in a 23-dimensional space. They placed them as far apart as possible, so even if the signal got a little scrambled, it would still be closer to the right point than any other. That's how we fix errors from billions of miles away.
All right, moving on to lesson 3, the butterfly effect. And here we're shifting gears. We're moving from static shapes to systems that are constantly in motion, changing and evolving, often in ways that are totally unpredictable.
So what you're looking at here is the famous Lorentz system, a very simple model of weather patterns. We're starting 2 simulations with conditions that are almost identical. They differ by just 1 part in 100,000. At the beginning, you can't even tell them apart, but it doesn't take long before they just fly apart. This crazy sensitivity to tiny changes is the very definition of chaos.
And of course, you get to bring this to life yourself in the next coding exercise. You'll actually simulate the Lorentz equations, plot the system's journey through its phase space, and create that iconic, beautiful butterfly shape. It's the perfect geometric picture of chaos.
Okay, for our last big lesson, we're diving into the deep end. We're heading into the strangest arena of them all, the quantum world. In Lesson 4, we're going to learn how to find our way around Hilbert spaces, the infinite dimensional landscapes where quantum mechanics lives. Now this quote right here, this is a total game changer. It basically says that designing a quantum computer program isn't really about abstract math. It's a geometry problem. Building a better quantum algorithm is the exact same thing as finding the shortest possible route between 2 points on some complex, curvy surface.
When you translate it like this, suddenly the quantum world feels a lot less weird and a lot more like geometry class, but in a good way. Superposition? That's just combining points in space. Entanglement? That's just when points are linked together in a way you can't pull apart. And a quantum algorithm is just finding the most efficient path from point A to point B.
The exercise for this one is seriously cutting edge. You're going to use a real quantum algorithm called VQE to figure out the most stable structure for a molecule. But what you're really doing is searching for the lowest point on a high-dimensional energy landscape. You're basically turning a super complex chemistry problem into a geometric search for the lowest point in a valley.
All right, let's take a breath. We've journeyed through these vast, empty spaces. We've found hidden shapes in our data. We've mapped out chaos, and we've navigated the quantum realm. Now it's time to put it all together and forge your new geometric mindset.
So, what did we learn? This whole journey really boils down to 4 huge insights. 1, high-dimensional space is massive and mostly empty, so we need clever new ways to explore it. 2, our messy, complex data actually has a simple, hidden shape, a manifold, that we can find. 3, even chaotic systems have a hidden order, a geometry that controls them. And 4, computation isn't just about ones and zeros. It's about finding the shortest path through a geometric space.
And that brings us to the real punchline. Learning to see the world this way, it's not just some neat academic trick. The ability to find these hidden geometric shapes and navigate them, that's what separates someone who just uses an algorithm from the person who invents the next world-changing one. This, right here, is the toolkit you need to build the future.
So I want to leave you with this one final thought, this one big question. If all computation is really just geometry, what amazing new solutions are just sitting there waiting for us to find them? What world-changing problems could we finally crack if we only knew the right shape to look for?